This battery is completely full, and it still cannot start the car. Nothing inside is broken, nothing leaked. It is just cold. Today, one lithium battery goes on a lie detector at 3 temperatures, a freezer at -20, a lab bench at 25, a heat chamber at 45. It is the same LG cell we raised against sodium last time, and this test will pull one number out of it. At -20, that number does not just rise, it explodes, more than 10 times over. And here is the twist to stay for. The version of this battery that looks the healthiest on every reading is the one that is quietly dying. Let's run it. The lie detector is called impedance spectroscopy, and it is gentle. We whisper a tiny wiggling current into the battery, fast wiggles, then slower still, and we listen to how hard it pushes back at every rhythm. Drawn as a curve, that answer becomes the battery's fingerprint, the Nyquist plot, and you read it left to right like a sentence in 3 parts. The left foot is the plain resistance of the wiring and the liquid. We call it R0. The arc in the middle is the hard part, everything that fights the charge as it crosses the battery's inner surfaces, the entry step plus the thin film sitting on the graphite. Engineers lump it into one name, the charge transfer arc, and the long tail is ions crawling deeper inside. Diffusion, foot, arc, tail, that is the whole language. We are running it on the published physics model of this exact cell, the same model battery labs use. At a comfortable 25 degrees. The whole fingerprint spans about 16 milliohms, and the arc part is 11. Hold on to that 11. In 30 seconds, it becomes 110. Now we chill the same cell to -20 and ask again. Watch the foot first. It slides right from 2 milliohms to about 6. The liquid inside has gone thick and syrupy, so every ion swims slower, 3 times worse. Annoying but survivable. Now watch the arc. It does not grow, it detonates. 20, 50, 80. We have to zoom out 10 times just to keep it in the frame. 110 milliohms. The exact step where charge enters the electrode just got 10 times harder, and we did not tune anything to get this. It falls straight out of activation energies measured on this cell and published, 40 kilojoules per mole at the graphite side. Frozen cells in real labs agree, and some measure 20 times or worse. So picture your phone in a winter pocket. The energy never left it, but under load. The voltage now sags so deep that the phone reads empty and shuts itself down for protection. Warm it up, and the charge walks right back. Nothing was lost. It was locked in. But why? What are the ions actually doing? Let's shrink down and watch. Every lithium ion travels wrapped in a coat of solvent molecules, about 4 of them held on tight. To enter the electrode, the ion must strip that coat off right at the door. And stripping the coat is the single most expensive step in the whole battery. Now watch the 3 doors. At 45 degrees, coats fly off, and ions pour through like a revolving door. At 25, steady traffic. At -20, look at the queue. Ions pressed against the door, coats stuck on, waiting. In this entire scene, not a single one has made it through. That queue at the door is your exploded arc. Same fact, seen from inside. There is a law underneath all of this, and it is one of the oldest in chemistry. Arrhenius law. The rate of a chemical step falls exponentially as temperature drops, and every step has a price tag, its activation energy. So let's test our own data against it. We fit a simple circuit to every fingerprint, 19 temperatures from -30 to +60, and pull out the arc resistance each time. Then the classic move, plot 1 over the resistance, against 1 over the temperature. If Arrhenius is truly in charge, 19 scattered points should fall on one straight line, dead straight. And the slope hands us back a barrier near 30 kilojoules per mole, sitting right between the graphite door at 40 and the cathode door at 24, exactly where a cell with 2 doors should land. And the paper's own lab measurements run even higher. The simulation never memorized that law. The physics inside it did. So heat must be the hero then. Warm the cell to 45, and the arc shrinks to half of its room temperature size. At 60, a third. Every door swings easier. Faster charging, more power, happier gauges, which sets up the most dangerous idea in this whole story. If hot batteries test this well, why not keep them hot? Because impedance only measures how easily charge moves today. It says nothing about tomorrow. Inside the hot cell, the side reactions obey the very same Arrhenius law, and they speed up too. The protective skin on the graphite, the SEI, a rust-like film that eats a little lithium as it grows, thickens faster and faster. In a famous open dataset, the cells cycled at 45 degrees showed the smallest, prettiest arcs, and they died first. In one same cell study, 260 cycles cost 4% of capacity at 25 degrees and 13% at 55. Rule of thumb, every 10 degrees hotter roughly doubles the aging, the same doubling law that spoils milk. The hot cell wins the beauty contest and loses the war, and the difference is cruel. The cold cell's pain is reversible, warm it and it heals. The hot cell's damage is forever. That one asymmetry writes every battery rule you have ever been given. Rule 1, never charge a frozen battery fast. Draining it cold is merely slow. But when charging cold, lithium arrives at a door that will not open and piles up outside as raw metal. Plating, it is permanent, and it can grow needles that pierce the cell from inside. This is exactly why an EV heats its own battery on the way to a winter fast charger. Spending a few percent of range on warmth nearly doubles the charging power waiting at the plug. Rule 2, the fridge is not the enemy. Cold storage is genuinely good for a battery. The same frozen chemistry that blocks power also blocks aging. Cold only hurts the battery you are using. And rule 3, this rule follows you off the planet. The rover batteries on Mars obey the same instruction printed on your phone box. Do not charge below 0, so NASA keeps them warm through the Martian night. One honest footnote, this cell's parameters were only measured down to about -5 or -10. Our -20 point is the law extrapolated, and real electrolytes turn even nastier down there. So reality sits above our curve, not below it. And plating and SEI growth are not inside this model. Those numbers came from the experiments we cited. So here is the whole story on one stage. One cell, every temperature, each fingerprint standing where its temperature lives. Toward heat, the arcs calm down into little hills. Toward cold, they rise into a mountain range, 60 times taller at -30 than at +60. This is what temperature does to a battery in one shape, and it is not just our simulation. A real 64 amp-hour cell, measured in a lab at every temperature from 0 to 45 and published last year, draws the same mountain. Cold batteries are slow, hot batteries are liars. A battery lives longest right where you do, between about 15 and 35 degrees. So next winter, when your phone gasps and dies at 30%, smile. The energy is still in there, waiting for warmth. Last time, we raced lithium against sodium on this same lie detector, and in the cold. Sodium plays a very different game. That video is on screen now. Subscribe, and I will see you there.